Hello and welcome to another video. Today we will be learning about properties of functions. Let's start with some basic properties of functions that we already know back from Algebra 1 and Algebra 2. The first one is going to be the x-intercept. I do want to go over the other names that are used for the x-intercept. We can also call it the root or the roots. We can also call it the zero, and we can also call it the solution. All of those four names mean the same thing. So where your graph either touches or crosses the x-axis. So as you can see on the graph on the screen, we have one x-intercept here, another one here, and a third one here. When I write my x-intercept, my roots, my zeros, or solutions, I do like to put them in the form x comma 0. In this case, we are going to have to approximate because as you can see on the graph, they don't cross at an exact point. So we'll do our best to approximate where the zeros, roots, x-intercept, or solutions happen. So the first one is going to be around negative 1.8, comma 0. Again, I like to write them as an ordered pair. The next one is going to be around negative 0.3, comma 0. And then the third one is going to be around 2.8, comma 0. For y-intercept, it's going to be similar, but instead of where it crosses or touches the x-axis, it's going to be the y-axis. So looking at my graph, I can see it cross right about there. For the y-intercept, I am going to do it backwards. It's going to be 0, comma y. And looking at my graph, again, I'm going to approximate. So it's going to be around 0, comma 0.9 or 0.9. Again, that's going to be the very basic one that you already know, and then we'll learn some new ones that you haven't seen before. The next property that we are going to be talking about is going to be when your graph is either increasing, decreasing, or staying constant. This one's going to be the hardest one to understand because it is a little bit weird. When you say increasing or decreasing, you're talking about what your y values are doing, but you describe them over a domain using your x values. Again, it's a little bit confusing, but it makes more sense if you look at it with the graph as an example. So what I like to do first to show if my graph is increasing or decreasing, I like to put arrows next to my graph, and all the arrows should always point to the right. So this is kind of what my graph is doing. Then it goes up, then it comes down, goes up again, and then comes down. So the first part is asking where the graph is increasing. So as you can see, this arrow is pointing up, and this arrow is also pointing up. So I know I'm increasing in this general area somewhere, and I'm also increasing in this general area. Like I said before, we are going to describe increasing and decreasing with the x values or over a domain. So I'm going to say my graph is increasing from x equals this number to x equals this number. So to find exactly where the graph change, I'm going to color code. I'm going to highlight only the increasing parts first. So let's do blue for increasing. So again, I can see that my graph is going up here, and then my graph starts going up here, and then it stops. So looking at my graph that's highlighted, it started increasing at x equals -3 first, and then it stopped at x equals -1. When we do increasing or decreasing, we always use parentheses. You will see why in a little bit, because this point is part of both the increasing, but it's also going to be part of the increasing. So you can't say that it's increasing and decreasing at the same time, so we just exclude it completely. You will learn a little bit more about it in calculus and how to find it. But for now, we're always going to use parentheses for increasing and decreasing. So again, I'm going to start increasing at x equals -3, and then I'm going to stop increasing at x equals -1. I'm going to put a comma because I have another piece that is also increasing. It starts increasing at x equals 2, and then it stops increasing at x equals 4. So open parentheses, 2, 4. You can also follow it with your pencil, right? Start at -3, and then you can see your y values are getting higher, higher, higher until you get here. After that, they start coming down. Same thing here, you start going up, up, up. They get higher, higher, or larger, up until here at x equals 4, and then they start decreasing. So now let's look at the decreasing part. I'm going to highlight using a different color. I'm going to do green. Again, I can see my graph going down. I can see my graph going down because of the arrow. And I can see my graph going down on the last piece. I don't see any constant, so that's not going to be part of my answer on this one. But we will do some in class, like that have constants, where it just looks like a straight line. So for the decreasing, or my green pieces that are highlighted, I start decreasing at -4, or x equals -4, and then I stop at x equals -3. Put a comma because I have a few more pieces that are decreasing. So I start decreasing at -1, and then I stop decreasing at x equals 2. And then for the last piece, I start decreasing at 4, and then I stop decreasing at 5. So we actually covered the whole domain because our graph is either increasing or decreasing, right? Excluding the points where it changes, as you can see. You can also think of it as having a negative slope and a positive slope. So when you have a negative slope, you are decreasing. When you have a positive slope, you are increasing, as you can see on the blue or the green shaded areas. We will do more examples in class and talk about how to put your arrows and practice that. And then we'll practice how to write the whole increasing, decreasing with any given graph. The next thing we're going to be talking about is extrema. So extrema is actually divided into 4 different parts. And extrema just means where your maximums or minimums occur. You already saw maximums and minimums back in Algebra 1 or Algebra 2 when we looked at parabolas. You had a minimum and then you had a maximum, depending on which way your parabola was facing. So this time we can actually apply that to any given graph. Like I said, extrema is divided into 4 different parts. We're going to have our local, or relative, max. We're going to have our local, also known as relative, minimum. We're going to have our global, also known as absolute, max. maximum, and then we'll have our global, or again, absolute min or minimum. So these two words are interchangeable depending on which one you want to use. I like to use both because, again, we don't know which one will show up on the test. Sometimes it will say relative maximum, sometimes it will say local, depending on the question that you're working on. Or you can see both as well. So what does the word local mean? Like your local store. So local means around the area. So that's what local maximum is going to be. It's going to be the maximum number around the area. Same thing for minimum. We're going to have our local minimum or relative minimum, and that's going to be the lowest value around the area. When we talk about global, it's going to be the opposite. It's going to be the highest out of the whole graph. When we talk about absolute minimum, we're talking about the absolute lowest point on the graph. So we're going to figure out how many extrema we have on this graph, and then we're going to label them accordingly to see in which one of these categories they fit. Something important about maximums and minimums: a maximum is going to occur when your function changes from increasing to decreasing. Again, back from algebra 2 or algebra 1, remember your little parabola that was upside down? You can see how it's increasing here, and then it starts decreasing, and then that creates this point at the top. Same thing, your minimum, that will happen opposite when your function is decreasing and it starts to increase. Same thing, you can see your y values going down, down, down up to here, and then up, once they get to that point, they start going up. So it's pretty easy to identify them once you remember when they happen. So looking at my graph, I can see that my graph was decreasing here and then it started to increase. So this is going to be an important point that I have to worry about, because it is going to be an extrema. Then it starts increasing, going up, 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 up until here, and then it starts coming down. So I have another extrema here. Now I'm going to start decreasing, decreasing up until here, and then I'm going to increase, giving me another extrema. I'm going to follow my graph again, increasing, 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 changes to decreasing one last time, giving me my fourth and last point of extrema. Like I said, we're going to look at when it changes from increasing to decreasing, create a maximum, or when it changes from decreasing to increasing, creating a minimum. So the first one, I'm decreasing and then increasing. You can also think of it as this point is the lowest point around the area. So that's going to be a local minimum. Then I'm going to put the order pair, which is -3, comma, -2. After that, I'm increasing, I start decreasing, or you can see that is the highest point around the area. So this is going to be a relative. Again, I can use the word relative or local maximum, and it will happen at -1, comma 1. Hard to see. After that, I'm decreasing, decreasing, and then I start to increase, creating another minimum. So I know that's a minimum. But the thing that is different about this minimum is that there's nothing below that point. Not a single one. When you look at this one, it was a local relative, because if you look at the graph, there's a whole set of points that is lower than that one. But when you look at this one, there's absolutely nothing below it, making it a absolute minimum, and it will happen at -6. Sorry, 2 comma -6. And then our last point is going to be increasing, and then it starts to decrease. So that tells me that it's a maximum. And then that one is going to be a global maximum, because again, there's nothing higher anywhere in the graph that will tell you otherwise. So global maximum at 5, 4. So again, it's pretty easy. I like to put them on the graph, but you can also write them over here on the side if you want, so that way it looks less messy, up to you. Okay, so looking at the last property, we are going to be talking about even, odd, or neither functions. So meaning that a function is going to be classified into 3 categories. The first one, even, the second one, odd, and then the third one, neither, meaning it's not even nor odd. If you have a graph, it's pretty easy to identify them. Even functions are going to be symmetrical about the y-axis. So y-axis is going to be your line of symmetry. And the way that I like to think about odd ones, to make it easier to wrap my head around it, is that they're symmetrical once you do it along the x-axis and the y-axis. I will explain what I mean with an example because it's easier to understand. So looking at example 7a on the screen. So what do I mean by symmetrical about the y-axis? So meaning that I'm able to fold it, and then every single piece will overlap with each other once you fold completely. So looking at A, I know this graph is not going to be even, because that's very easy to see that nothing is going to overlap with each other. Like I said about odd, it's kind of weird, but if we do it one step at a time. So if I were to take this graph and reflect across the x-axis, this part right here would look opposite way. And then if I were to fold it again and reflect the piece that I just drew, we're only going to do it with half of it. And reflect again across the y-axis, this line or this curve will actually look like that, and you can see how they overlap. So this is going to be an odd function. Looking at B, again, I'm going to check if it's even by looking at my y-axis. If I were to fold, then this line will overlap with this one, that curve with that one, and then the last one will do it as well, meaning I have an even function. And then looking at the last one, again, I can see that this line would be my line of symmetry if it was even. Nothing will overlap because it will look something like that. Right? That one would be over here. And then let's try the trick about taking half of the graph and reflecting it across the x-axis and y-axis and see what happens. So if I reflect across the x-axis, this line only, it will look like that. And then after I reflect across the x-axis, it will look like that, meaning this one is going to be neither. If you do have an equation, you can use these two equations to figure out if it's even or odd. If none of these equations work, then it is going to be neither. We kind of practiced this in class the other day, right? So looking at example 8a, to check if it's even or not, I am going to set it up as f of negative x equals f of x. So when I plug it in, I want to use my f of x, that's at the top, and then replace every x with a negative x. So absolute value of negative x minus 2. Since I only have a negative x inside the absolute value, I can actually get rid of it. And then I want to make sure that is equal to my original equation. In this case, it is, because once I drop that negative because of the absolute value, it will be equal to my original. So now I know that this equation is even. I don't have to check for odd, because if it's even, I know it cannot be odd. Looking at B, let's check if it's odd, even, or neither. So let's check if it's even first. So again, f of negative x is equal to f of x. So I'm going to take my original equation, and everywhere I have an x, I'm going to replace it with negative x. So negative x cubed minus 3, and I want to make sure that is equal to the original. When I cubed a negative, the negative does stay, so that will be negative x cubed minus 3, and I want to check if it's equal to the original. There's an extra negative on it, as you can see. So B is not going to be even, but it could still be odd. So let's check if it's odd or not. So I'm going to erase this real quick. Now I'm going to use the second equation at the top to figure out if it's an odd function or not. So the second one says if my f of negative x is equal to negative f of x. If they're equal to each other, then I do have an odd function. So last time I didn't have to do anything on the right side. Now I do because of this negative. So just make sure you distribute it accordingly. So on the left side, I'm going to take my original equation. Everywhere I have an x, I'm going to replace it with negative x. So negative x cubed minus 3, and I want to figure out if that's equal to negative times f of x. So again, I like to put my parentheses and then put it inside, and then distribute my negative. In this case, again, I have a negative x to the cubed power. I am going to keep my negative equals, and then when I distribute, I get negative x cubed plus 3. So as you can see, they are different. So it's also not odd. So my answer would be neither. Again, you have to kind of check both, unless you find the correct one right away, and then you don't have to worry about it. Looking at C, I'm going to check if it's odd first, because I'm going to require the most work. Get it out of the way. So again, f of negative x equals negative f of x. Those are the equations that you do have to memorize. They are not on your formula chart, but they're not hard to remember. Okay, so on the first one, I'm going to take my x's and replace them with negative x's. So 2 times negative x cubed minus negative x. I'm trying to figure out if that's equal to negative f times the whole f of x, which is 2x cubed minus x. Don't forget, I have to distribute my negatives, so I'll put my arrows to remember. So looking at the left side, I keep my negative because it's taken to an odd power or a cube. So that will be negative 2x cubed. And then I have two negatives here, which will become a positive x. I want to make sure, I want to check if it's equal to negative 2x cubed minus times the minus, which will give me a plus x. So they are the same. And again, we're checking to see if it was odd, which in fact it was. So I don't have to do anything else. Hopefully you learned something. Thank you for watching, and I will see you all next time.